Welcome back to ModeMind. Building directly on our exploration of mechanical forces, we are shifting our focus to a critical system that puts friction to work every single day: belt pulley mechanics. Understanding exactly how belts and pulleys interact is absolutely crucial for transmitting mechanical force efficiently through complex machines. By mastering these dynamics, engineers can directly control speed, manipulate torque, and maximize the overall performance of industrial machinery. Let's break down the science behind how these systems keep our world moving. To truly grasp how this works, we must first look at the fundamental concept of how a belt pulley system functions. At its core, power transmission is entirely driven by torque transfer via friction. The belt is wrapped tightly around the pulleys, and as the driving pulley turns, it relies on the frictional force between the two surfaces to pull the belt and turn the secondary pulley. To prevent the system from spinning uselessly out of control, proper belt tension and pristine surface conditions must be maintained to ensure effective power delivery without any slippage. This dynamic relies heavily on three key parameters: the diameter of the pulley, the total tension of the belt, and the specific coefficient of friction. Together, these variables act as the control knobs that dictate the mechanical capability of the drive. During operation, the system establishes two primary forces known as the tight side tension, T_1, and the slack side tension, T_2. The tight side carries the brunt of the heavy load, while the slack side remains at a lower tension. Carefully balancing these two opposing forces is what allows the system to achieve peak performance without tearing itself apart. When we perform a deeper force balance analysis, the mathematical relationship between tension and torque becomes incredibly clear. The relationship between the tight side and slack side tensions is governed by Euler's formula, expressed as, where mu represents the friction coefficient and theta is the wrap angle in radians. This math reveals that the difference in tension is exponentially amplified by the friction and the amount of contact area. Because of this exponential relationship, there is a critical angle required to ensure stable force transmission. For the system to maintain a reliable grip and prevent sudden, dangerous slippage under dynamic loading, the belt must wrap around the pulley by a minimum of 120 degrees or 2 pi 3 radians. Once that grip is secure, the actual torque equation can be calculated. The usable rotational power generated by the system is the direct product of the force difference between the tight side and the slack side, multiplied by the pulley's radius, r, which is written as. This elegant equation perfectly demonstrates how the straight, linear tension forces traveling through the belt are successfully converted into clean, usable rotational motion to power a machine. Looking closer at the role of friction, its primary job is preventing slip entirely. The coefficient of friction, mu, is highly dependent on the specific materials being used, typically ranging between 0.3 and 0.5 as standardized by ISO 1813 to 2015 guidelines. Understanding this value is vital because a dangerous sliding condition occurs the exact moment the tension ratio, T_1, T_2, drops below the exponential threshold of E_mu, theta. When this drop happens, the belt loses its grip and begins to slide independently of the pulley, destroying the system's efficiency. To accurately calculate these limits, engineers rely on a uniform distribution assumption regarding the contact pressure between the belt and the pulley surface. Advanced 3D finite element method studies have confirmed that assuming a uniform pressure spread across the contact zone is highly accurate, providing the mathematical foundation needed to design reliable industrial machinery. The physical design of the belt itself has a massive influence on these mechanics, dividing the industry into two main types: flat belts and V-belts. Flat belts are characterized by their ability to maintain low bending stress during high-speed operations, but they limit maximum tension capacity to about 15 megapascals. This unique profile makes flat belts ideal for high-speed, light-load systems, covering roughly 35% of modern industrial conveyor applications. On the other side of the spectrum are V-belts, which are specifically engineered for enhanced friction and higher tension capacities. A V-belt features a wedged profile that actively forces itself into the grooves of the pulley as it rotates, creating a wedging action that increases friction and provides over 30% more tension capacity than a flat belt. Because they can easily handle 50% more demanding mechanical loads, V-belts dominate about 65% of the force transmission market, serving as the go-to choice for heavy-duty industrial systems and automotive engine drives. Even the best designed systems must constantly contend with dynamic loading effects like vibration and mechanical fatigue. The most stressful moment for any belt occurs during system startup, where tension can fluctuate wildly by PM 10% to 15% of the nominal tension value. These sharp startup spikes introduce severe transient stresses that accelerate early wear on both the belts and the metal pulleys. Over time, this constant cyclic loading directly dictates the fatigue life of the material. Under standard operating conditions, a quality belt can reliably endure up to 10 million, 10 to the power of 7, tension cycles before structural failure becomes critical. However, operating at a high loading frequency can sharply cut that lifespan down by 40% to 50%. To combat these destructive forces, manufacturers build viscoelastic properties directly into the belt materials. This built-in material damping absorbs the shock of rapid movements, reducing destructive resonance amplitudes by 30% to 40% and significantly lowering vibration-induced fatigue to prolong the system's life. To measure how well a system is performing, engineers look closely at efficiency metrics, specifically targeting power loss and slip. Under ideal tension and alignment conditions, a modern belt pulley system is incredibly efficient, boasting a transmission efficiency rating between 95% and 98%. This exceptionally high efficiency is vital for minimizing energy waste across large-scale industrial operations. The remaining 2% to 5% of power loss components are primarily caused by three things: internal friction heat generated during rapid movement, the continuous bending stresses as the belt rounds the pulley, and minor slip losses where the surfaces fail to maintain a perfect, synchronous grip. To monitor this, advanced facilities use encoder differentials for real-time slip detection. By constantly comparing the exact rotation speeds of the driving and driven components, systems can detect if the slip ratio crosses a critical 3% threshold, instantly alerting maintenance teams that significant slippage is occurring and accuracy is dropping. Avoiding these losses requires careful pulley design considerations, focusing entirely on geometry and material selection. Cast iron completely dominates the industrial market, making up over 70% of all manufacturing pulleys due to its outstanding tensile strength of approximately 250 megapascals. This robust metal provides the extreme durability and structural resistance to deformation required to sustain crushing mechanical loads over years of constant use. For systems utilizing V-belts, selecting the correct groove angle is critical to maximizing the wedging force. Roughly 85% of V-belt pulleys are manufactured with a precise groove angle between 30 degrees and 40 degrees, optimizing the contact pressure and ensuring the highest possible power transmission efficiency without binding. Finally, the surface finish of the pulley must be perfectly maintained. Engineers recommend a smooth surface finish with a roughness, R_A, of less than 0.8 mm. Keeping the metal this smooth reduces frictional wear rates on the belt by up to 40%, vastly extending the lifespan of the belt while maintaining a flawless grip. When proper maintenance is neglected, the system will inevitably experience specific failure modes, categorized by wear, slip, and fatigue. The absolute leading cause of premature belt wear is mechanical misalignment. Industry studies show that over 70% of all premature belt wear cases are directly linked to a structural misalignment exceeding a tiny 1-degree angle, highlighting just how sensitive these systems are to poor installation. The second major failure mode, belt slip, is almost always linked to a sudden loss of operational tension or environmental contamination, with these two factors accounting for nearly 60% of all recorded slip incidents. Lastly, mechanical fatigue cracks are highly localized. Over 65% of all structural fatigue cracks form directly within the sharp bending zones of the belt, where the material experiences the absolute highest levels of continuous cyclic stress as it wraps around the pulley radius. To prevent these costly breakdowns, operations implement high-level optimization strategies designed to maximize total system reliability. The first line of defense is automated precision tension control. By integrating smart, automated tensioners into the machinery, the system can actively adjust itself to keep the tight side tension, T_1, within a strict PM 5% window, completely neutralizing slippage and ensuring perfectly consistent power delivery over years of operation. The second strategy focuses on material upgrades. By replacing standard rubber belts with advanced materials infused with high modulus fibers, industrial plants can reduce belt elongation to less than 1%. This structural rigidity minimizes mechanical losses and dramatically enhances the belt's capability to sustain heavy dynamic loads without stretching out of shape. Finally, maintenance teams deploy proactive monitoring tools like infrared thermography. By scanning the running machinery with thermal cameras, technicians can easily spot friction hotspots forming on the belts or pulleys long before a visual crack appears, allowing for timely, scheduled maintenance that prevents unexpected catastrophic failures and keeps the factory running flawlessly.